Okay guys, so playing Where in the World is Narc today. Narc is at a car dealership. So if you hear a lot of random background noises, that is why. So this video is going to be about the position versus time equation and graphs. So the position versus time equation, you might see written as d equals vi, the initial velocity, times time, plus 1/2 a, the acceleration, times time squared, where d is the distance or displacement. On the reference table, it's written as x, meaning the final position, equals x0, the initial position, plus v0, the initial velocity, times time, plus 1/2 at squared. So it's the same equation, just slightly different variables. Okay, so again, this is our final position, so our ending point. Okay, this x0 represents our initial position, meaning where we start. And for most of our problems, this is usually going to be 0. Okay, v0 is your initial velocity. Okay, so remember, if we start at rest, the initial velocity is going to be 0. Okay, the acceleration is a, and of course t is time. Okay. Now if we're doing this with positions and velocities, remember position, velocity, and acceleration are all vectors, which means that the direction matters. The acceleration, so these are all vectors, again, which means direction matters, so you got to watch out for positive versus negative. Very, very important. Okay, so just a few things to remember. Okay, with position or displacement, because they're essentially the same thing. Okay, let's talk about what positive versus negative means. So positive position means you are to the right or up or east or north of your starting point. Negative position means you are left or down or west or south of your starting position. Okay, so if you are an object traveling downwards, you should be plugging in your position as negative or getting a negative direction or a negative answer. Okay, so positive velocity versus negative velocity. Okay. So positive velocity tells us we are moving right, up, east, north. Okay. Negative velocity tells us we are moving left, down, west, or south. Okay. So position gives us where we are, velocity tells us how we're moving, acceleration, positive versus negative, tells us about our net force. Okay, so if we have a positive acceleration, that means our net force is right, up, east, or north. If we have a negative acceleration, that means our net force is left, down, west, south. Now notice how I didn't say that positive acceleration meant speeding up, negative acceleration means slowing down, because that is not true. Okay, so if you want to know speeding up versus slowing down, okay, we need to have the velocity and acceleration in the same direction. So either positive velocity, positive acceleration, negative velocity, negative acceleration. if we are slowing down, velocity and acceleration need to oppose each other, right? Just like if you need an object to slow down, you have to apply a net force opposite of the direction it's moving. Makes sense. So these need to be in opposite directions. Okay, so positive velocity, negative acceleration, negative velocity, positive acceleration. So that's it for the equation, and we can use this equation to help us figure out some information about a position versus time graph. Okay, so our equation is x equals x0 plus v0t plus 1/2 at squared. Now there's two ways we can use this equation to create a graph. We can either use it to create a graph for constant velocity, okay, or constant acceleration. So remember, it's not enough to say that an object moves constantly. You either have to have it move with a constant velocity or constant acceleration. So remember, if we're moving with a constant velocity, acceleration is 0, which makes our lives a little bit easier because that whole last term of the equation can go away, right? Because if a is 0, then there does not need to be any acceleration term. So let's figure out how this translates to a graph. And it might be a little bit better or easier if we write it as v0t plus x0. So if we're writing a position versus time graph, that means x is on the y-axis, which is strange, and t is on the x-axis. So in my equation, if I replace x with y and t with x, okay, this looks very similar to y equals mx plus b. So that tells me that my initial velocity is my m value, or my slope. And that tells me my initial position is my b value, or my y-intercept. Okay, and this is the equation for a line. So if I have a position versus time graph for constant velocity, I should have a lovely line graph. Right? So position is x, time is t. So if I have an object moving with a constant positive velocity, right, that graph would look like this. And this graph would have an initial position of 0. Okay. A constant negative velocity might look something like that. And this would have an initial position of not 0. Okay, so both of those objects are currently to the right of the origin, so their position is positive. If I wanted to extend this graph downward, I could draw some more graphs. Okay. So this object would have a constant negative velocity because my slope is negative. It would have an initial position of a negative value, and it would end up farther away. Okay. And then I could also draw a graph like this, right, where we still have a negative initial starting position, but we move closer to the origin, so we're moving right, and this would have a constant positive velocity. Okay. And it makes sense that the slope tells me about velocity, because if I do TSA for this graph, right, T's for the title, it's always y versus x.
Okay, perfect.
So x versus t. Slope is always y over x. So in this case, x over t. Any position over a time is going to give us a velocity. Area is y times x. And in this case, x times time. And a meter times a second is not anything. So that's our graphs of position versus time for constant velocity. Not really that interesting, but can give us a lot of information. Where things get super fun is when we have constant acceleration. Because with constant acceleration, we need to use the entire equation, because we have to have that a term. Okay, now again, I'm going to rearrange it in a way that we might see it in math class with that t squared term first. Okay. So remember, x is on the y-axis, t is on the x-axis. So this is actually y equals 1/2 ax squared. This would be 0x plus 0, which is actually a quadratic equation, right? The whole idea that y is ax squared plus bx plus c. Okay, so remember this plus c is our y-intercept. So that means our y-intercept for this graph is our initial position. Okay, the b value gives us our initial slope. Okay, so our initial slope is based off of the initial velocity. And the a value here tells us about our parabola, specifically how wide it is or how quickly the slope of the parabola changes. So that's all going to be based off of 1/2 times the acceleration. Okay. So let's take a look at some position versus time graphs with acceleration. So the most common graph we're going to see is something that looks like this, our standard parabola. Okay. Our initial x position is 0, so we're starting at 0. Our initial slope is 0, so that means our initial velocity is 0. And you see how we are kind of curving upwards in a smiley face? Okay, that means our acceleration is positive. Okay. So think smiley face, positive acceleration. And in this graph, the slopes are getting steeper and steeper. So for this graph, we are speeding up. Okay. So another graph we might see is one that looks like that. Okay. So again, we still have an initial position of 0, but this time our initial velocity is not 0 because the slope of this line right here, the tangent line, is definitely not 0. It has some positive value. Okay. Our acceleration, if you look, this kind of makes like a little sad face. Okay. So when we see that sad face graph, our acceleration is negative. Okay. So our slopes are getting slower and slower, or less steep as time goes on, which means our object is getting slower and slower and slower, which means we are slowing down. And that makes sense because velocity and acceleration are in opposite directions. Okay. So let's take a look at another graph. So another graph we might have is one that looks like this. Okay. So in this case, we have an initial position that's negative, okay, because our y-intercept is negative. It looks like our initial velocity, the slope at this point, is 0. Okay? And our acceleration, we have half a sad face, so our acceleration is negative. Okay? Now, because we don't have an initial velocity, it's tough to tell whether or not we're speeding up or slowing down based on opposite signs, but we can look at our graph and our slopes get steeper and steeper and steeper as time goes on, so we are speeding up. Specifically, we are speeding up in the negative direction. And the last graph we can take a look at is one that looks like this. Okay. So for this blue graph, we have an initial position that is negative. My initial velocity is 0. Okay. I have an acceleration that is positive because that's a happy face. And my slopes are getting steeper and steeper and steeper as time goes on. So that is also speeding up. Okay, now you might be thinking, well, how are we speeding up? We end at 0. Remember, this gives us a final position of 0, not a final velocity of 0. If we want to know about velocity, we look at the slope. So we would look at the slope of the line tangent to the curve, so to speak. Okay. Let's do one more graph. Purple sounds good. So one more graph that we might have is one that looks like that. Okay, so that purple graph has an initial starting position of 0. It has an initial velocity that is negative because that has a negative slope right there. It points downward. My acceleration, well, that looks like half of a happy face. My acceleration is positive, which must mean this object is slowing down because my velocity and acceleration are in opposite directions. So this would be an object slowing down in the negative direction. So an object that's moving in reverse but hitting the brakes. And that's basically all there is to know about position versus time graphs, where everything comes from. Don't forget to tie the equations to the graphs because that's going to help us a lot. So remember, constant velocity is going to give us line graphs. Constant acceleration is going to give us parabolic graphs because of the equations and the fact that we have the x squared term when we have the acceleration, and the fact that we don't have an x squared term when we have a position. Okay.